In this video lesson, we're going to be looking at the rules for drawing Lewis dot diagrams and then doing some examples. So this slide right here will talk about the steps for drawing Lewis dot diagrams. It's probably a good idea to have these rules down when you're learning on how to draw Lewis dot diagrams. After a while, you won't have to look at these rules so often. Real quickly, let's just run through the 6 steps that I've written down for drawing Lewis dot diagrams. I don't expect you to know these rules or how they apply perfectly right now. You'll start to see them applied when we start doing some examples. But nevertheless, here are the steps. The first thing you'll want to do is you want to look at a chemical formula and determine the central atom and place the terminal atoms or outside atoms around the central. Now, how do you know what atom in a formula is the central atom? Well, the long story short is after some practice, you'll quickly start to see what atom is the central. However, here are some things you can look for. A lot of times, the central atom is the least electronegative element in the compound. It's the element that there's only one, and/or it's the element that's written first. And I say and/or because it doesn't necessarily mean that all 3 of those have to be the case. Those are just some general patterns. A common element that is the central atom is carbon, particularly when you're looking at organic compounds. However, there are other atoms that can be central as well, so those are the key things to look for. Once you've figured out what your central atom is and you've placed the terminal atoms around it, step 2 has you counting up your total number of valence electrons in the compound. Be sure to add electrons or subtract electrons depending on if you're looking at a cation or an anion, and we'll look at examples of that. Then what you're going to do is you're going to bond all of your outside or terminal atoms to the central using a single bond. You know there has to be at least a single bond. There may be double or triple bonds, but we'll get to that later. Remember that each bond stands for 2 shared electrons, and so you're going to subtract this number from your number that you found in step 2. Then what you want to do is you want to complete the octets for your terminal atoms with any remaining valence electrons that you may have. After step 4, if you still have electrons left over, put all of those electrons on the central atom regardless of how many there are. So no matter what, whether it's 2 electrons, 8 electrons, it doesn't matter. Stick them all on the central atom. And then finally, you're going to use multiple bonds, in other words, double or triple bonds, if you need to in order to complete the octet for any element where necessary. So like I said, those are the steps. I don't expect you to understand how those work right now. We simply just have to apply them to examples so you can see how they work. Before we get started on some examples, 2 questions to ask yourself when you have drawn a Lewis dot diagram to confirm that it actually is a valid Lewis dot diagram. If you can say yes to both of these questions, you know you've drawn a successful Lewis dot diagram. First question is, did you draw the same amount of electrons that you started with? So for example, if you counted in step 2, your total number of valence electrons is 20, then your Lewis dot diagram you drew should have 20 electrons. If it doesn't, if it has more or less, you've drawn something incorrectly. And the second question is, are the octets for all your atoms satisfied? That's important. If there's an element that doesn't have a satisfied octet, then you've drawn an incorrect Lewis dot diagram. Now this is for another video, but I do put a note here that just because you can answer yes to both of these questions and you have a successful Lewis dot diagram, that doesn't necessarily mean the diagram you've drawn is the best one, but we'll get to that in a later video. So the last thing I have here before we get into some examples are some helpful tips and hints, and this was really going to help you when you start drawing structures more often. When you have an atom that's in the terminal position, meaning it's not the central atom, but it's an outside atom, halogens are going to have single bonds. So chlorine, fluorine, iodine, if they're in the outside position, they will have single bonds. I don't have it listed there, but hydrogen also will have a single bond. Hydrogen can never have a double bond or a triple bond. So this also includes hydrogen. Group 6A elements, for example, oxygen, sulfur, etc., if they are in the terminal position, they're going to favor a double bond. Now the key word there is favor. That does not mean they will have a double bond, but you're going to find later on that they like to have a double bond. And we'll talk about why later. And then group 5A elements, nitrogen, phosphorus, they're going to favor a triple bond. Once again, the key word there is favor. It doesn't necessarily mean that there is a triple bond. So just some helpful tips and hints just to keep in mind. But without further ado, let's just get into some examples. So let's take a look at the first one, CH3Cl. You've got 3 elements there, carbon, hydrogen, chlorine. The first step of those 6 steps that I showed you is determine what the central atom is and then place the terminal atoms around it. So hydrogen can never be a central atom. It can't be. So it's either carbon or chlorine. Carbon is going to be the central atom. I know that for a few reasons. One, it's written first. Carbon and chlorine, there are only one of each, so that they're both possible contenders, but carbon is written first. And if you compare them, carbon is the least electronegative. And remember I said carbon is a common central atom. Very rarely is carbon a terminal atom. So knowing that, that means I'm going to place carbon in the center, and then I'm going to place my terminal atoms around it. There are 3 hydrogens. So I'm going to place 3 hydrogens around the carbon. And then a chlorine is the other terminal atom. So it doesn't matter if you write chlorine here versus in any of the other positions, because we're just looking at the Lewis dot diagram right now. We're not talking about geometry or anything like that. That'll come later. So right now, that's perfectly fine. So the next step then is to count up my number of valence electrons. Carbon has 4 valence electrons. Hydrogen has 1 valence electron, but there are 3 of them, so total there are 3. And then chlorine has 7. So total, we have 14 valence electrons to use. So that means our Lewis dot diagram that we draw needs to have 14. Okay, step 3 is we need to start out single bonding our terminal atoms to our central. So that means I'm going to draw single bonds between all of these terminal atoms and bonded to carbon. Now, how many valence electrons did I just use making those single bonds? Well, remember, a single bond accounts for 2 valence electrons each. So I just drew 4 bonds, and so that means I just used 8 electrons. So out of my 14, I just used 8 electrons, which means I have 6 electrons left over. So what am I going to do with those 6 leftover electrons? Well, the first thing you want to do, this is step 4, is you want to make sure your terminal atoms are satisfied first, meaning those octets are satisfied. Remember, hydrogen is happy or satisfied with 2 valence electrons. It's one of those exceptions. It doesn't want 8 and it can't have 8. It's not large enough. So all of my hydrogens are satisfied. So I'm going to put a little check mark next to there just so you can see that they are satisfied. So I don't need to do anything with them. However, chlorine is not satisfied. Chlorine wants 8, and right now it only feels 2 electrons around. And so what I'm going to do is I'm going to take those 6 electrons that I've got and I'm going to start placing them around the chlorine. 2, 4, and 6. Oop, you can't see that 6th one. There we go. So by doing that, I have used my 6 valence electrons, and now I have 0. Okay, I don't have any other valence electrons at my disposal. But I did, by adding those 6 electrons onto chlorine, I did make chlorine happy. And so I don't have any electrons left over. And so that means that if I have to satisfy any more octets, I can't add electrons because I don't have any. I would have to use some double or triple bonds. But I may not need to. The only other element I have to satisfy is the carbon in the center. And does carbon have 8 valence electrons? 2, 4, 6, and 8. It does. And so chlorine actually is already satisfied. So I don't have to do any double bonds or triple bonds because everything is satisfied as of step 5. Also notice, remember I said when halogens are in the terminal position, like right here, they want single bonds. And hydrogens all want single bonds. So that was another indicator that I was good. So that is a valid Lewis dot diagram. Now on the test, you don't have to draw the check marks. I was just kind of showing you that. But just so you can see that you don't need to put that there. You can just see that they're satisfied. So let's look at the second one. H2O. So even though it's not written first, oxygen is going to be the central atom in this one because hydrogen can never be a central atom. And I'm going to write hydrogen to my hydrogens because there's 2. I'm going to write them in the terminal position. So second step, let's count up how many valence electrons I have. Remember, hydrogen has 1 valence electron, but there are 2 hydrogens. And so that means 2 valence electrons there. Oxygen has 6 valence electrons. So total, I have 8 valence electrons to use. So step 3 is I'm going to start out with single bonds from my terminal atoms to the central. I just used 4 valence electrons drawing those single bonds. 2 valence electrons from this and 2 valence electrons for that. So that means out of my 8 valence electrons, I used 4, and so I have 4 left over. Step 4, after you've drawn your single bonds, that's step 3. So step 4, make sure your terminal atoms are satisfied. Hydrogens are both satisfied, so I don't need to do anything there. So then what am I going to do with these remaining valence electrons here since my terminal atoms are all set? Step 5 says that if you have any remaining electrons, regardless of how many there are, stick them on the central atom. When there's an even number of valence electrons, do it in terms of pairs. So 4 valence electrons left over, I'm going to put 2 here, and then I'm going to put 2 here. I'm going to always put them in pairs. So that takes care of those, and so that means I have 0 electrons left over. They're all on the Lewis dot diagram. So now, let's make sure that my octets are satisfied. I've already satisfied the hydrogens. Is the oxygen octet satisfied? And the answer is yes. Oxygen has 2, 4, 6, and 8 valence electrons. So that's all satisfied there. Now I didn't do this in the first example, but I will do it here just so you can see. Remember, always do that check. Ask yourself those 2 questions. So those 2 questions were, and I'll go back real quick. Did you draw the same amount of electrons that you started with? And are the octets satisfied? So let's look at the second example that we just did as an example here. So first of all, I had 8 valence electrons at the beginning. Do I have 8 here? 2, 4, 6, 8. I do have the same amount of electrons. Are all the octet rules satisfied? Yes. Hydrogens are satisfied and oxygen satisfied. So that's how I know that I have a valid Lewis dot structure. All right, let's look at this third example, O2. Now this one's kind of weird because there's not really a central atom or a terminal atom because it's only 2 elements bonded together. So not really a central or terminal. So we're just going to kind of just go at it. Oxygen has 6 valence electrons, but there are 2 of them. So that means I'm going to have 12 valence electrons total. Okay. Even though there's not a central or a terminal, I'm still going to start with a single bond. Okay, just start with a single bond, get it started. So that means out of 12, I just used 2, and so now I'm down to 10 valence electrons. At this point, you'd want to take those electrons and start satisfying your terminal atoms. Well, they're both terminal, so just pick an oxygen and start going for it. So here's what I'm going to do. I'm going to do 2, 4, 6. Okay, so satisfying that oxygen, I use 6, and so now I'm down to 4 electrons left. So now I'm going to start satisfying this oxygen here. 2, 4. Okay, now, some students might get excited and they might keep going. They might say, okay, 2, 4, 6, yay, this oxygen is happy now. However, that's too many electrons. Count how many I have. I've got 2, 4, 6, 8, 10, 12, 14. I have 14 electrons in this structure, but I can only have 12. So that's how I know that I did something wrong. So these actually need to go away right there. And so what am I going to do here? Because by putting on those 4 electrons, I'm now down to 0. But clearly all the oxygens or all the atoms aren't satisfied. The oxygen on the left is satisfied, but not the one on the right. The one on the right only has 6 valence electrons. So I can't add any more electrons, so what do I do now? The only thing you can do is you can start moving electrons into multiple bonds, whether that be a double or a triple. So here's what I'm going to do. This oxygen right here, if I were to take these 2 electrons and take them off that oxygen, so I'm going to move them there, and what if I put them over here? Well, the problem now is the oxygen on the right is satisfied, but not the one on the left. So we've really just created the same problem, just on a different oxygen. So here's what happens. I'm going to put these electrons back originally where they were. This oxygen on the left basically says, look, I'm not going to give you my electrons because then that means I'm going to be unsatisfied. But here's what I will do. I'm going to take these 2 electrons and I'm going to share them in the middle. Okay, so what does that look like when you share those? What that means is you are now taking those 2 electrons off of the oxygen right on the left and you're sharing them now in the middle, and that forms what we call a double bond. So look at what I've done here. First, let's count up how many electrons we have. 2, 4, 6, 8, 10, 12. And then 12 electrons was how much I had at the beginning, so I know I have the right number of electrons. And then are my oxygens satisfied? Well, 2, 4, 6, 8, this one's satisfied. And 2, 4, 6, 8, this one's satisfied. So they're both satisfied. So I've drawn a valid Lewis dot diagram. Also notice, Even though there's no central atom, they're both terminal in this case. Notice what kind of bond oxygen had. It was a double bond. And remember what I said back on this slide is group 6A elements, oxygen of which is one of them, they favor a double bond. And so that makes sense that this one would have a double bond. So for timing, I'm actually going to go ahead and stop this video. In the next video, I will go ahead and continue with the other three.